Okay, awesome. Thanks, Harvey. All right. So, this is the on Pharma HPC workshop with showcasing a couple of selected examples. And as you already know, my name is Michael Meyer. I'm a solutions engineer here at POSIT and a colleague of Phil, who did a nice introduction. This is just a few more things of me, so you also get a bit more background who I am and who I am not, which is also quite important for you to know. So originally, I'm a scientist by training, so I did a PhD in theoretical astrophysics. However, then over time, I changed into IT, and about 3 years ago, I landed here at POSIT, where I'm the solutions engineer. Before POSIT, amongst doing a PhD, I spent 10 plus years at 2 large pharmaceutical companies in Basel, Switzerland, and I've been working both on the IT business side, both in research and development. So, I'm aware of quite a bit of the pharma landscape to some extent. And that was also one of the reasons that brought me to POSIT, because back then we were a customer of POSIT. So also to be very transparent, I'm definitely not a data scientist. I'm not a statistician. I'm also not a software developer per se. So I'm sure there's many people in this audience that are very infinitely more skilled in those things than me. However, I think some of the knowledge that I bring with HPC, that still could make it very worthwhile to go through this webinar. Okay, so here's just a real quick agenda, and at some point we also open it up to keep it very dynamic and interactive. So the first 4 points here will be me mostly talking, explaining things, and after which you will then get access to the HPC system, and then you can explore things on your own, and also follow along the 2 examples that I brought along. That's the ClusterMQ package and future.mirai, which is a fairly recent addition to the future ecosystem. Okay, so before we go really deep in HPC, HPC, as you know, stands for high performance computing. And if you work on a highly performant, super fast computing system, we all probably know that having mundane tasks such as package installations can sometimes extremely slow, particularly if you're using R environments or naively installed packages on the R front, but also pip install on the Python front is quite slow due to its sequential nature. And however, as of the not so very recent future, 2 packages have emerged. On the R side, it is a package called PAK, P-A-K, that a colleague of me and Phil is developing. And on the Python side, there's a package called UV that is more recent than PAK, I think. And what those tools are doing is they are downloading and installing packages truly in parallel. And that makes it much faster. PAK, in addition, also solves another problem that sometimes you will probably all have come across when you install R packages, that some R packages have operating system dependencies. If you don't have them, then the package installation will fail. With PAK, you can automatically detect if you have enough permissions, install those operating system dependencies without even looking back. And for reproducibility, PAK also can create a log file like you are probably used to from the renv package. Likewise, UV is to some extent a pip replacement, but also much more. Because it's a pip replacement, you still can use your requirements.txt file without any problem, just making use of the enhanced speed that you get out of it. For those of you that already are using RENV, I mean, there's also good news because RENV and PAC can be used together by setting this environment variable RENV config PAC enabled to true. And then every time you initialize or restore any R environment, RENV will automatically call PAC to do all of the installation, and it'll be also very fast. You will see that later on in the hands-on material. All right, so I mean, this is also for the last time that I will mention Python. So all the other material are going to be related to R. With that, maybe let's move on. This is just a brief reminder what HPC is. As I already mentioned, HPC stands for high performance computing. And quite often it's also a synonym for high performance computing clusters in general. There is a couple of important concepts, and you will get to know them in a bit more detail in the next couple of slides. There's so-called scheduler or resource manager, and I listed a couple of names. Today we will mostly focus on Slurm. However, there's also those other mentioned schedulers. A HPC cluster is an infrastructure that consists of various nodes. So we have compute, submit, and master nodes. Typically, such a HPC cluster comes with fast parallel shared storage. If you have a super fast compute environment, then you don't want to wait forever until your slow storage is supplying the data or writing out the data. There is programming paradigms around multi-core and in general distributed computing along the lines of OpenMP and MPI. Some clusters use an application stack, so-called software environment modules. Maybe some of you already came across that. If you have to, environment modules are used if you have to use commands like module load and a certain software name in order to make that software accessible. There's also important thing that the network needs to have a very low latency and high bandwidth, and why that is more in a little bit. Before I go on, I mean, just here is already a glimpse of what we will see later. Typically, if you take your program, you parallelize it, and you run the same program/algorithm on a number of different processes, here ranging from 1 to 1024, then you typically expect that if you run it on, for example, on eight processes, that it should be 8 times as fast. And as you can see here with the blue line, that is the actual measured speed up. It is very close to the ideal speed up quite a while. However, at about 128 cores or so, something is happening. That makes it less. The speed up is decreasing again, and why that is, we will get to in a moment. In addition, and maybe that's already a bit too much technical details, because those algorithms are running distributed over different servers, the so-called compute nodes. They at some point have to communicate with each other. And so there's the important concept of network latency that you should be aware of. And here, for example, I have taken 3 typical networks that you see: Gigabit Ethernet, InfiniBand, and an Amazon-specific thing called EFA. And I did a little bit of a thought experiment where I'm taking a data packet of size X, so that's the X-axis from 1 byte to 100 megabytes, and I send this across those 3 types of networks, and I measure the time it takes to be transmitted. And this is just theoretical data. But however, what it shows you, number one, for large packet sizes, the time for transmission increases linearly, because that's where the bandwidth of the actual bandwidth of the network comes into play. However, for small packet sizes below, let's say 10 kilobytes or so, 10 to the 4 bytes here, you will all see that the time for the transmission is pretty much flat. And the flatness comes from this network latency, because no matter if you, for example, let's look at the purple line, the most upper one, no matter if you send a packet of size 1 byte or 10 kilobytes, it always will take 10 to the minus 3 or 1 millisecond to send that stuff. And if you now later on, if you then think that a processor on one server needs to talk to a processor on a different server, and in a processor, we all know that frequencies are gigahertz, so things are happening on a nanosecond time scale roughly. Having a millisecond time scale for network communication means that the processor, unless it's really doing lots of things, before having to communicate again, can become quite efficient. It can become quite inefficient. And I mean, that's one of the reasons why many supercomputing centers, they are investing in this InfiniBand network, which as you can see here is the lowest line here, which has the lowest latency of about one microsecond, 10 to the minus 6 seconds. I mean, 10 to the 1 microsecond and 1 nanosecond is still 3 orders of magnitude away, but it allows for much better performance in terms of scalability. All right, so this is that part. And I mean, now here's just something that, I mean, that's a logical picture of a HPC cluster. You have, like here, I've painted 6 boxes. So typically you have a login node, the red box over here, where the users can log in. You will also get such a thing later. Then there's a head node, and then you have many compute nodes. And all of that stuff at the moment is just sitting there, and we don't know what's happening. So let's make something happening. Before I go, I mean, there's also the concept of a submit node. And that means any node that is able to submit a job to the cluster. And in general, all of the login, head, and compute nodes are typically submit nodes. However, from a user perspective, for the most of the time, jobs are being submitted from the login node directly. Okay, so now, I mean, one of you will come along and say, oh, I want to run my R or Python program. Okay, here's another mention of Python. Then what happens? I probably should tell you that on the head node, Slurm has a so-called controller daemon. And this knows everything about the so-called compute nodes. So you see an example that compute node 1 has currently 24 cores, 32 gigs of memory, and 10 of them are in use and 12 gigabytes of memory. And so it has availability of some sorts. Then the others, I mean, this is just an example here. And this controller daemon now on the head node really knows, keeps track of which compute node is having which resources available and running which jobs. So this is the thing on the head node on compute node side. Well, now you as a data scientist, you're still sitting on the login node and want to run your R program. Good. So I mean, how can you run that stuff? So I mean, and this will be a big part later on as well. You need to know how much resources your R program will need, and we will have an example on how you can find that out. So here, for example, I know the Opera program uses 2 cores and 20 gigabytes of memory, no GPUs. So what's happening now? So you will tell that to the controller daemon on the head node, and that will then say, okay, let me find out which compute node can handle that. And you can see that the only compute node that currently can run that job is compute node 1, because that is the only one that has 20 gigabytes available. All the others have less memory available. And in terms of cores, we only need 2 cores, so compute node 1 has 10 available, and so that's all fine. And I mean, that means that the controller daemon on the head node will decide, okay, this program runs on compute node 1. Okay, so I mean, this is really like a 101 in resource management. That is the same for every HPC scheduler. What I just thought it would be good for everyone to have a quick refresher on how this all works together.
Hey, Michael, sorry to interrupt, but is it possible to share the slides with people? Do you have a link to them?
Sure. Let's maybe go back to the slideshow over here. So I mean, for Slurm, there's many commands that you would need to know if you would be able to interact with it on the command line. So, however, I mean, I just select a couple of them that I think are extremely useful. Namely, there's a commands sbatch/srun that allows you to submit interactive and non-interactive jobs. If you want to submit stuff, you also want to cancel or kill jobs, so that's done with scancel. And there's a command sinfo to list available queues and partitions. SQ lists your currently running jobs and the status, and with scontrol show job, giving you more job details. And I mean, maybe that's just helpful for those that are not 100% familiar with the Slurm syntax later on. Okay, so typical workflow, how you would interact with the CLI scripts, CLI commands. I mean, typically you would write a little script, for example, this little bash script, call it submitter.sh, where you put in those 2 lines only, assuming that you had an R code locally in your current working directory. And you then can submit that script or job to the cluster via the sbatch command, where you just tell them to the submitter.sh, like the script, and it will then tell you, yeah, I submitted a batch job with this job number, and then that's the point where the scheduler is aware, and the scheduler will then see, like we described earlier, where it can run that job. While the job is running, you can check your running jobs via the sq and scontrol commands. And if you think that the job is not working or is stuck or hung, you can use the scancel for canceling or terminating the job. All right. So I mean, if there's a running job, if there's jobs on your cluster, then there's maybe three main states that are very important. There's a R state, which means the job is running, everything is normal. Sometimes the job can be in pending state, and that's PD, because I mean, sometimes if the cluster doesn't have the resources you need available immediately, your job is being put in a queue, and if and only if the resources become available, your job will actually run, so it will be stuck in the pending state. And a job that you will probably not see much, job state, is CG, like for completing. The job is ending, but it's still writing outputs. So sometimes if you have a slow storage device, then you may see lots of jobs in the CG state. All right. And I mean, of course, my example that I just showed here, S-batch submitted as H, that was very simple because it doesn't, I haven't told the cluster how much resources I need, no nothing. And I spent the last 20 minutes or so telling you how much knowing about the resources is important. So of course you can supply or specify how much resources you need via this -n and -mem option. So here like our previous example job, or the example that I showed you for resource management, you then add the -n for number of tasks, which are equivalent to cores in most cases, -mem 20 gigabytes, and then you have your you also can specify standard out and standard error files here, and eventually you specify that script that I have modified a little bit here. So you see no longer it's a bash script, it's a direct R script, where in the first line, I'm just specifying which R version I want, and I've specified the direct path to the R script binary. And the Slurm will then just execute this submitted R as a R script with that version. Okay, so that's that stuff, and of course, you can put this approach even further, because sometimes you don't want to remember that your job took 2 cores and 20 gigabytes of memory. So you can even add this add those resource requests in different lines that are comments to R, for example, or to bash. So you start a line with hash and then S-batch, and then you specify all of those previous command line arguments like -n2, -mem 20g, and so on and so forth. And if you then just run S-batch submit 2.r, then it will run as before. And it will automatically submit a job with 2 cores and 20 gigs of memory. All right. So, however, all of the examples that I showed so far, we are always with a probability of success close to 100%. So here I'm trying to submit a job with 2 cores and 128 gigabytes of memory. And I mean, it's not clear to you yet, but none of my compute nodes has 128 gigabytes of memory. So what happens in that case? I will get a feedback from S-batch, memory specification cannot be satisfied, job submission failed. And I think it's probably not surprising. However, I mean, it's important to know that if you're exceeding the physically available resources on your HPC cluster, then you will get such an error. Okay, and I mean, following on that, so as you just saw, if the cluster does not have the requested resources at all, the job submission will fail. If the cluster, however, has got the resources, but they are not available at the moment, the job will be queued, so job will be in a pending state. And 2 more things, because getting your resource needs right can be tricky. So if your actual job launches more processes than you have requested in terms of number of cores or tasks, the code will still run, but it will run slower because the cluster will only give you access to, let's say, 2 cores, and if you have requested 4 cores, if your job runs 4 processes, those 4 processes will fight for those 2 cores, which is typically not very efficient. To the contrary, however, if your job consumes more memory than you had requested, your job will be likely terminated or killed by Slurm, because unless having more processes fighting for the same CPUs, if you have allocated 1 gigabyte of memory and your code tries to use 2 gigabytes, memory is not easy to be shared, so your job will be killed. All right, so now this is adding a bit more meat to the bone, as we like to say. How do I know how much resources I will need? So the way how it's typically done is that you can run a small version of your job and measure its resources in order to, and you can use that to extrapolate how much your big job will need. And the measure of resource needs can be done in various ways. One of them is there's a R package that another colleague of mine and Phil has written named Syrup. You see the link in the slides here. Sometimes HPC admins also provide dashboards where you even can show the real-time resource consumption of your Slurm job. Can be helpful. And in the past, for example, I mean we use that to detect some memory leaks of some software, which can be quite interesting. And you also, however, can use the Slurm CLI for your previous jobs to get information. And here I just show you one example using the SACCT command, which stands for Slurm accounting, where you can specify job ID and then select which variables of that job you want to specify. So here I selected the job ID, the elapsed time from start to finish. RSS is the maximum amount of residential memory, so that's typically what we should be concerned with. The job state and the exit code. So if exit code is not 0, then you know that your job had an issue. All right. And I mean, it's always important to remind everyone that you only should use as much resources you actually need. Some extra safety margin are still okay. And also do not forget that you run on a shared system and others will also want to get things done. So if you request a multiple of the resources that you actually are using, your job will still run perfectly fine. However, I mean, others may not be able to use the unused parts of your resource allocations, and they will suffer from that. All right. So, I mean, this is maybe just, I know it's still foundational, and now I just want to go one step further, because many of you are doing data science projects of some sort, and here I just thought about that during such a data science project, you have various stages where you're writing documents, we are doing coding, we are doing code review and stuff like that. So from a compute resource need, you have different stages where you have low, medium, or high resource needs. And however, we all know that that in times when your resource need is very high, you may realize that your model needs to run such a long time because it's so complex, and you really are looking into ways how you speed it up using parallelization, for example. I mean, just to make sure that you can run your model before your deadline approaches, for example. And quite often you will also have things where you need to iterate your model sequentially. So if every model you have to wait for 1 day, I mean, then it's probably not making much progress. So if you can reduce the time from 1 day to 1 hour, then the problem is much more manageable. You're making much more progress scientifically. All right. This is a disclaimer, and I mean, I didn't explicitly say, I mean, as always, there's no excuse to not write performant code to start with. So optimizing for performance, even without parallelization, is always highly recommended, because parallelization should only be used on codes that have been reasonably optimized before attempting parallelization. Yeah, and then, however, parallelization of parts of your code can still speed up execution though. And we know that as a data scientist, you don't want to spend half a year optimizing your code. You want to get scientific results. So sometimes it's also okay to, if you want to have a brute force thing and you just want to parallelize that because you only run it once. So, I mean, as we all know, the world is neither black nor white. I mean, there's different shades of gray as always. All right. So now, I mean, I think you probably are also aware for the following, we will be using POSIT Workbench as a tool that has been integrated into HPC cluster. And here is, for those of you that are more interested in the technical way how Workbench works, just a quick rundown. And so you have the POSIT Workbench thing on the top left. That's what you will also see later, where you can log in via web browser, and then you can launch some sessions. The sessions are here orchestrated by the POSIT launcher that will convert the resource requests into a language that is compatible with one of the many compute backends. And you see we are supporting Kubernetes, Slurm that we use today, Spectrum, LSF, and Altair credential. And the launcher will then, for us today, will use Slurm to submit a job onto a compute node and where the interactive session will run. We will also use something called Workbench jobs that I will explain later. However, as you may see from the bottom right corner, there's this Workbench job thing down here. And if you trigger a job here, it will spawn a new job using the launcher again in the separate Slurm job. So this is very high level, and now I just want to discuss the background and Workbench jobs that you have here. Workbench jobs are already mentioned. Background job is another thing, and doing interactive code development, sometimes you need to do test runs on smaller data or subsections of the code. And this is where, and if sometimes the code is much, if it takes long interactively, the R console is blocked and you cannot proceed. However, if you put it in a background or Workbench job, then this will run in the background and unblock the R console for any further work.
Michael,
Yeah.
sorry to interrupt. Are you sharing something on your screen because we don't see it at the moment? And one other question, there's a question that had come up in the chat.
Sure.
as well.
Okay, let me see. Let me see it.
Oh, maybe it was me. Sorry.
Yeah, I mean, yeah. I mean, the question from Yusuf about how does Slurm distribute jobs across cores, especially when I use parallel loops within the R function. Yes, I mean, if it's okay with you, can I defer that question because you will later on see a real example how that will be done. And yeah, I think that was the major question here. Any other questions?
And apologies, the slides are okay. It was just my setting.
Okay. Okay, fair enough. All right, and I mean, for later, it's also here important to understand what the difference between background jobs and Workbench jobs are. Background jobs, they run as child processes within the same sessions, and they can be seen and monitored by the current session. Only all of those jobs will terminate if the session is closed. And the nice thing about background jobs, though, is that they because they run within the same session, you can forward the environment variables back and forth between the job and your main session. So if you have a long-running job running as a background job, that means if you enable forwarding of environment variables, that job gets all your global environment variables as input and will copy back all the new variables back to the session. And this is available in open source RStudio as well. Now, workbench jobs are slightly different because they run as completely independent process. On Slurm, they will run in independent Slurm jobs. They are globally available. They can be seen and monitored in all sessions. And because they're separate jobs, they will keep running if the session is closed. Unfortunately, no possibility of forwarding environment variables. And this is also only available in POSIT Workbench and will be specific in RStudio and VS Code only. And one of the benefits that you will see in a moment is those workbench jobs allow you to submit jobs without ever using the Slurm CLI. All right, so oops. So, and this is how it looks. This is just a session launch. I think you all are familiar with that. Maybe let's go a little bit faster. And now if you, for example, work on your code, you want to submit a workbench job, then you have this graphical user interface over here where you supply your resource needs as well. Click on start and then your job will run. I will show you in a moment how that looks like. Good. Okay, and I think now I think it's the time for a little live demo. I mean, I will do the live demo and then I will share the information for how to log into the HPC system, and that will give us or bring us up to the first hour where we will make a 5 or 10 minute break, and then we'll come back with 20 more minutes of theoretical background, and then we can go in the real hands-on if that's okay with everyone. Okay, so I mean, as you will see later, there's this URL over here, on pharmamayor.cx. I mean, you don't have any credentials yet. That will change later. So if I click a new session, I want RStudio Pro. I have various resource profiles. I go with a medium profile, click on Start Session. Session is starting, and I should have RStudio IDE running in a moment. Here, there we are. All right. Now let's get rid of that. Okay, and now let's create a new script. And I mean, I will just write a little for loop that simulates a long-running job. So like this. And I will use a very simple thing. Sys.sleep 2. So I will just print all the numbers between 1 or 10, sleep for 2 seconds. And of course, if I run that stuff here, you will see it's doing the thing, printing all the numbers. So now let's do it, do something. Let's sleep every 5 seconds. Let's go up to the 100 mark. And let's save it as a sleep.r, for example. Then let's go. I mean, if I would run it now, then it would go to 100, sleeping 5 seconds in between. However, now I want to submit it as a workbench job. So you click on the workbench tab down here, click on Start Workbench Job. You see it's already pre-filled with all the things that you need, which R version you're using, which code you want to run. And maybe let's just stick with a small And if I click on Start Now, then you see a new line pops up here. It is running now. And if you click on that running job, you can trace the standard output here. So how do you know that this is a separate job? If you go to the terminal over here, then you see that now a new job has started over here in this all partition that's running now. So and now, of course, this is a long running job, and I don't want to wait this to finish. So I terminate my RStudio session here. Now session is shutting down, is completely gone. However, you see the workbench job is still running. And if I click on this thing here, I still can trace the standard output of that job over here, which I think is quite neat. And likewise, if I'm going back and start a new session, let's see that stuff. It's active. Right, then you see I'm back over here. If I click on the workbench jobs tab, then you see things are still running. Okay, so I mean, just wanted. I mean, this is a very simple example. Later on, you can explore things more with either with your own codes or with some of the codes that I have prepared, and we will get you later. All right, so this is that stuff. Let's just, okay, now I will just scroll a little bit forward. I mean, this will now tell you how you can get access to the environment. I think the process is as such, you click on the first link, that will open a Shiny application that will tell you your username. You can browse to this pharma.cx URL that will get you to the login page. Put in your username and the password, which I will paste in the chat because I don't, or you can copy off the slides depending on how you prefer to do things. There's the chat window again. Okay, let's wait quickly to stop sharing. That's the password, yeah. Okay, and I mean with that, I think that should give you a few moments either to get in, get set up. One thing that you can do, and we will do it together after the break, if you already want to be half a step ahead. So if you are in the workbench, already, you open a RStudio session, you go to the terminal. If you then type this command here, git clone, then this will give you access to the material that we will use once we come back from the break. We'll come back to that. Maybe to answer also the other question that Rebecca asked, do I have to use POSIT Workbench to use Slurm? I mean, not really. POSIT Workbench can work standalone or with many other compute backends such as LSF, Kubernetes, and so on and so forth. If you are a programmer and you want to use Slurm, you can use it without POSIT Workbench. If you, for example, install open source RStudio and make that integrated somehow in your Slurm HPC class, so that's all possible. The benefit that you will get from POSIT Workbench, however, that I think you have access to the so-called workbench jobs that I just showed. And I think in general, you have a reasonably good integration in your tools that will allow you increased productivity and so on and so forth. Let me just share back my screen and we at least do the cloning together. So I hope that you all have seen how I open the RStudio Pro session. I just typically select a medium size because medium is neither small nor large. I open that thing will come to life. It will get me straight to the RStudio session. And then you have on the left bottom, you have the console terminal workbench job pane. I click on terminal and then I just paste the git clone thing over here. And we should, because I already have messed up my thing. So yeah, I mean, I'll do it something before I move my old thing out of the way. And if I now do git clone, then you see all of the files are being downloaded from the GitHub repository, and you then can explore all of those contents here. Okay, good. So, Robert, before we get really hands-on, let me just go back to the slides. And I think that was a question, how does it all work with Workbench and Slurm and architecturally and stuff like that? So this is how it does. You as a user, you open your browser. The fact that you choose Google Chrome is in no way indicative of any preference, so whatever browser you have will be okay. You point to rnpharmamail.cx, which is this Workbench server. And on that Workbench server, two services are working: RStudio Server, RStudio Launcher. Where Launcher is this launcher thing that I told you earlier about. And so whenever you launch a session or a Workbench job later on, the RStudio Launcher will transform and eventually submit that job to the head node where the Slurm controller daemon is living. The Slurm controller head node will then decide which node it should run your RStudio session in that case, and will schedule and run it on that designated node. And however, having a session run on a compute node doesn't connect it to your web browser. So there's a callback happening through the POSIT Workbench server, and your web browser is then using this POSIT Workbench server as a kind of proxy to get through the session output. I mean, physically, however, the RStudio session runs on the compute node, and via this proxy on the Workbench server, you can access that stuff. That's one thing, and then the same. And as we discussed earlier, a background job is something that is being run within the same session. So you see the background job. I have just an arrow pointing back to the same session on the same compute node. However, if this RStudio session requests a Workbench job, then this RStudio session is talking back to the Workbench server, to the launcher specifically, and sending another resource request. And then the whole thing happens from start. After the request is sent, the launcher will convert it into Slurm compatible thing, submit a job, and it will eventually schedule and run, quite likely on a different compute node. And this I just realized that I forgot. So all the output will also be proxied via the callback to this main POSIT Workbench server here. So I hope that this answers the question that we had about architecture. Okay. Okay, and I'll just make a pause to check if people have issues setting up things. So let's just now go back to my little data science project synopsis here. And the question still remains, can I really run my model before the deadline? We still haven't decided on that stuff. And I mean, the answer is yes, you can. And I mean, you can do it twofold. You can leverage workbench jobs, where you can farm out your long-running job into different jobs, where you can use additional, even more resources than for your interactive session, like more memory, GPUs, and stuff like that. And because our studio session is already running on a submit node, you also can directly submit additional jobs from your session. So those are the two ways that we will explore. And I mean, the workbench job, I think I already showed to you, but how to use the RStudio session to directly submit jobs to this learn cluster is something we will investigate now. So here, I think that's the ominous slide 43 that contains all of the login information. So how are we doing? Is everyone able to log into the system, or do we still have issues? Still starting session. Okay. So let's check what's going on with session. Was it 009? I mean, I probably can also show you a little bit the backend. So here I'm logged on the HPC cluster, and if I'm running SQ to show the jobs, then you see there is a lot of things going on already, and you see many interactive sessions have a state of R for running, so you are all fine. However, you also see that there is 2 users, and I think, was it 0019 or 20? I mean, you guys, your job is in configuring state. That means something that I didn't explicitly tell you. This environment that we have here runs in the cloud in Amazon, to be specific. And typical features of a cloud is that the cloud is very elastic and is able to scale up and scale down your infrastructure as you need it. And I have provisioned enough compute nodes for to host up to 20 sessions. What I mean, depending on what session type you choose, it could be less. However, the 2 users that are in CF state means that the currently up and running compute nodes are not sufficient. So additional computers are configured. So typically this process is taking 5 to 6 minutes, and you see that just as we spoke, we have all of those users now in running state. That means that at the moment no one should have any problem. Or I will better go to the chat to make sure that this is true. Okay, succeeded. That's great. But okay. Okay, I mean, and we have Conrad just got in but could not pull in Git. Do you get any error messages, Conrad? Maybe if you want to type it, or maybe the problem has fixed itself. All right. Anyway, let's maybe just let's just go on a little bit. And I mean, now, finally, let's move closer to parallelization. And just a little reminder again, there's absolutely no excuse for writing performant code to start with. However, in this workshop, we are not optimizing any code. I mean, as mentioned, I'm not a software developer. I don't have 20 years of the programming experience and stuff like that. I can hack together codes, but for optimizing, you probably, I mean, there's other workshops and other sources of information you can use. Also, as mentioned, parallelization should only be used if local code optimization options are exhausted. As mentioned, sometimes there's brute force and and other edge cases where you just need to get things done. So in all of those cases, we can use parallelization. So before going hands-on, let's just also come back to one of the first graphs that you've seen, where I showed you the speed up versus the different number of cores for a given problem.
Sorry, Michael, there was a question in the chat from Yusuf.
I mean, local code optimization option. I mean, typically, I mean, you start writing a code that runs on a single server, maybe on your laptop and stuff like that. And by local optimization, I mean that you should make sure that the code runs as fast as possible locally without using any parallelization, because sometimes you already have quite a number of bottlenecks in your code, knowingly, unknowingly, and if you detect and fix those, sometimes you can speed up your code already quite considerably, that you even do not need any parallelization. That's what I mean, yeah. And I mean, there's tools that we don't have time today. There is Proflis, which is our profiler that you can use, that also has nice integration in the RStudio IDE, where you can really decompose your whole code and see how much time it spent where. If you want to get more information, I've done a different webinar with a colleague of mine from Novartis. So that's probably also all right, I will find that link in the next break and send it to you, because there we don't spend much time on parallelization as such. I mean, we are more focusing on optimizations, and there's a nice example where my colleague over time managed to have a 300x speed up with local code optimizations plus parallelization compared to the initial version. So that's something interesting. I will share that in the next break. Okay, cool. So let's go back to so I mean, here's what I wanted to explain. Very good. Thanks, Harvey. You beat me to it. Yeah. Parallelization. Naively, you would expect that if you have eight CPUs instead of one, your code should run 8 times as fast. And as you see on one of the very first slides, that's not necessarily true, because at some point there's a break where actual speed up is much smaller. So there was a scientist named Amdahl, and he just thought about given a code where a fraction p can be parallelized, 10%, 50%, 90%. The speed up on S processes can then be calculated at this little formula here. And while this is kind of not so intuitive, the interesting outcome here is that no matter how much processors you throw at such a problem, the speed up with unlimited number of CPUs is always limited by this fraction 1/1 minus p. And I mean, that means if you have a code where a fraction of 50% can be only parallelized, the maximum speed up that you will ever get with that code is a factor of 2. And that's the light blue line that you see in this little plot, because that asymptotically converges to 2. So, however, as the parallelization fraction increases, p turning towards 1, then you see that the speed up is the maximum attainable speed up is increasing quite a lot. And ideally, if you have p equals 1, then of course this would go to, as s goes to infinity, the speed up would also go to infinity in the same way. Okay, I mean, this is just a little thought experiment. If you think back again from the previous plot, you also saw that at high core counts, the speed up would go down again. So, I mean, I just, oops, I should go in slideshow mode again. I mean, Amdahl's law is nice, but it doesn't take into account things such as overhead from communication between processes. And that means that the speed up will increase close to ideal speed up, but well, at some point it will decrease again. And that's when there's more time spent in communication than in actual computation. And this also then ties back to the network latency that we spoke again earlier. So it takes longer to transfer 1 byte from one processor to the other than it takes to compute stuff. Okay, so I mean, parallelization is not magical, but I mean, of course, we need to have some tools to leverage all of those things. Good. So, I mean, now let's just cross over to a semi-concrete example using R. So let's assume you run on an RStudio session. You have in the RStudio session, you know you have an R version 4.41 is installed in a certain location. You have a working directory where you installed a couple of R packages. You write on a code.r, whatever that contains. And at some point, you want to make use of parallel computing. So here, I've got a little example that will make sense, much more sense later. So here's a typical cluster MQ call that uses so-called Q function that will basically take a compute function that you wrote, that you write and you want to calculate against the parameter n that ranges from 1 to samples, and you want to run that in parallel on 2 separate jobs. But that's what this command line is saying. And I mean, now I think we just break down in 3 steps what's now happening behind the scenes, and that will also help you later on to understand what you need to do when you really are engaging with distributed parallel computing. So, number 1, whatever this cluster MQ package is, it will need to submit a job and start a computation, or processes. So it will submit 2 jobs. That's what we told them to do, and within the job, it will start running our processes. And of course, we also, each of those processes or jobs will live in their own resource allocation for memory and CPU. Then of course, the R package or the R package needs to ensure that on the compute nodes that know nothing about the RStudio session, it uses or finds the same or compatible R version. It needs to ensure that the R packages are actually available. If you don't have shared storage, where should they come from, for example? And it also needs to have some working directory if needed. So I mean, let's assume that our package or cluster-MQ has figured all of that out. Now there's 2 R processes, ideally with version 4.4.1, running on compute node X and Y. There's shared storage available, so we can use the same R package and stuff like that. Everything is happy. So far, so good. Now this main process in your RStudio session will also automatically send some work to those 2 jobs, and they will now receive some work. They will be told, look, here's this compute function. I want to run this compute function against n equals 20. And when this is sent, for example, job 1 receives the work and munches it and then sends it back. So what do we need to make sure here is we need to ensure that the connections are actually properly established. R packages are available, and if needed, we need to export. We need to be able to tell those independent R sessions which R packages it has to use. Good. So computations are ongoing, and once they're finished, they will send back that result to this RStudio session. And this package then ideally will aggregate all of those results, because it will get samples results, because our index runs from 1 to samples. So it will get, if samples equals 100, we will get 100 individual results, and the package will merge it all in one data structure called results. Okay, that's what it says here. Now, one thing that you should be aware of, this parallel computing thing does not come for free. While the individual compute executions on those in those 2 Slurm jobs will probably not use much memory and CPU in general. However, let's assume that you have 10,000 samples, and suddenly the result data structure has 10,000 entities of a certain size. And then you soon can come into a region where this result data structure does not fit in your RStudio session, and you will get problems with resources there. So always when you write those functions, make sure that the return of those compute functions is as large, as big as no, as small as possible and as big as necessary. Okay. Now I think, I mean, now that I already talked about, now that I already talked a lot about the general concepts, using already some example, here is the first thing that we will look in today hands-on. So there's the so-called cluster-MQ package that has been around for a while. It is using the so-called zero-MQ protocol for fast and efficient communication. The good thing about it is all the operations are done without any transient files. So everything is done in memory or in network, which is helps to get to keep it fast with too much overhead. The operations are load balanced for additional efficiency. We will see that in a moment what that means. It supports various compute backends, for example, Slurm. And the really nice thing that makes cluster-MQ stand out, that all of the logic pertaining to the compute backend is stored in so-called templates. And by relying on those templates that are files that live outside of your code, it is extremely easy to take your code from your local laptop using cluster-MQ, with a local backend to a HPC cluster using Slurm backend, and you don't have to change your code. You only have very little or no code changes for your actual R code. And it also has to be said that it's mostly used for loop level parallelism, that are also sometimes called embarrassingly parallel jobs or codes. Good. And so here, if for those of you that want to take a load the code that I'm describing now, if you look in this workbench HPC, there's a subfolder cluster MQ, and if you open the compute.r, that should have the same function that I will go through with you now. However, if you just want to go through the results and a bit more explanation, it's already rendered Quarto document that you also can take a look at here. All right, so back to that presentations. So as I mentioned earlier, first we identify something we want to compute in times or samples time, and I've written a little function using the Palmer Penguin data set where I'm running a GLM model, looking for a model correlating body mass against species and sex of those penguins. I mean, that's not very spectacular. You probably have much better examples. So this is the compute function as such. And then I'm loading the library cluster MQ. I'm defining how many samples I want to run. Then I'm calling this Q function. And I mean, I'm giving it a couple of arguments. Compute is like the name of the R function. N is this this variable that I want to run. And then I just tell him also to run that in 2 jobs and a chunk size of 10. And give me back all of the results. And all of the other stuff is then post-processing. So if I go back to this thing over here, I mean, we can, if I run, hang on, now I think let's open this cluster MQ project first, because now you also can see we first need to install the packages. And please feel free to follow along on your environment. So now I'm in this cluster MQ subproject here. Now if I do run restore, then okay, it has been activated, so I want it to activate. It's restarting R, and I think it's let's use run restore again. And now you see this is already something that you probably don't have where you are working, because as mentioned about 1.5 hours ago almost, we have this Puck integration that is now installed as an additional package. And as a benefit, once that's installed, you see that the installation of those 69 packages that are needed to run this example are going to be much faster, because it first looks through all of the dependencies and then is downloading and installing things all in parallel. I mean, for those of you that are used to the speed of installed packages, I think this is slightly faster. And you also can see that it's installing things in parallel if you watch the standard output here. Okay, let's do that. almost done. Okay, now you see we have installed 22 packages and 47 dependencies. Now let's go back to open this compute.r thing. If I now run that stuff step by step, you see I'm defining the compute function, loading the package, and you see that it automatically even detects that we are running on a Slurm cluster, so all good. We are defining 1,000 samples, and we run this job over here, and you see, and here it's slightly different values. I'm running 20 jobs here to make it faster, but let's just change it to 2 and let's run it again, because then you also can see that there's actually jobs running. So we are running stuff here now. And if I go on the terminal thing here, then if I do SQ, then you should see that, there's other users also already running stuff, so that's great. You see that I have jobs here that are currently in pending mode. That means that the cluster is currently at capacity, and I mean, as some of those other jobs are finishing, our jobs will be run. Yeah, and for those of you that just want to see your own jobs, you can add the option $u$user here, and then that means only your own jobs are visible, and that tells me also that our things have already been run here. Cool. And if we then continue on, if I run the rest of the chunk, then it's doing a bit of post-processing, and eventually we arrive at a nice histogram of sorts. Yeah. So Rebecca, this is not an issue. I'm just using here all the default values of the cluster MQ package. However, if you were to set options, I mean, we can try that here. So if we put up here options cluster MQ skip the Slurm, and let's save that stuff, and let's restart that it does load the package. We run the stuff again. We set the option now. Okay, it takes a while. And now you see that error, that message that was bothering you is gone. I mean, it still tells you another feature that we have disabled here, but that's a advanced feature that you may need if you really do hardcore debugging, but for the purpose that we want to go today, it's probably not needed here. All right, so that's great. So let's go back to this little light show here. And I think one thing that Rebecca's question also already mentioned, I was talking about all of those templates, and I mean, you haven't seen any of those templates yet. So if you look in your home directory, you see one of those templates, and this is all used behind the scenes, really. This is this abstraction that I was talking about, that the cluster MQ package will detect which backend it's using, and then once it starts to start those processes, like I showed you earlier, it will use this as a template to submit those jobs. And here you have also the same hash sbatch things again in a slightly more complex writing. You have, because it's a template, you can replace any of those things with your own values. For example, mem per CPU line you have a memory, which is the variable you can set in cluster MQ. However, if you don't set it, it uses a default value of 1024, which is 1 GB of memory, and uses array jobs, number of CPUs per task, and so on and so forth. One thing is sometimes if the R interpreter is not in the path, it's useful to use that template because it will inherit the R home variable from the R studio session and will make sure that it finds the same R version again on the other compute nodes. Additionally, what you also can see here that this last command that runs the actual R process runs a single cluster MQ function, and this cluster MQ function is just cluster MQ worker with one argument master, and this master will then on the fly being replaced with the host name of the server and the port where this cluster MQ process this job was submitted from. So that means that, as I told you earlier, on those two compute nodes, the R process will be started. It will start a cluster MQ worker process that is only waiting until this process that's submitted a job will send any work. And besides that, it will just sit there doing nothing. All right, so that's this high-level overview. So another important thing as well is sometimes in your organizations, you are, of course, like you're not the only one on the cluster. So sometimes you want to run 100 jobs, like n jobs equals 100, because you have a big, long computation. Well, but the cluster only can run 40 of those 100 jobs at the moment. So with many other frameworks, your whole process would be stuck in the queue until 100 jobs would be able to run. Cluster MQ, however, is very flexible, that it will start distributing work as soon as only one of those worker processes is running. And that means that you can always submit ask for 100. If you only get 40, your code will still run with 40 workers. It will be a bit slower, but it's better to have a slower execution than no execution in that case. And for those of you that want to, sorry, let me backtrack. Two more things to be aware of. Like I mentioned earlier, the package is doing a great job of setting up the R process on the remote server. By the templates, it finds the right R version ideally. But you also need to export some variables, some global variables that your function may need. You can do that via the export function here. And likewise, you also can export names of packages that you want to use in the compute function. That's what I have written here via the PKGS environment, PKGS parameter. And of course, ClusterMQ has much more functionalities. For example, if you work a lot with data frames, then you can use the q_row function to do a row-wise calculation of things. I'll leave that up to you to figure out. And you also saw in my example, I'm using chunking. That will group batches of work together, and that can also improve or at least impact the overall performance of your computations as well. For those of you that are already have used heavily using for loops and sometimes are reaching out to for each, ClusterMQ also has a for each backend, so that if you load the ClusterMQ package, you use this function, register do parse CMQ, you can run your for each loop pretty much unchanged, and for each and ClusterMQ will distribute that work into those ClusterMQ jobs. And in the Markdown or in the quarter document that I have in the GitHub repository, you also find an example how that looks like. Because we are more likely you are all data scientists. We want to have the code reproducible. If you use random number generators and for each loops, do not use the do path operator with for each. Use the do RNG operator that comes from the do RNG package, because that will ensure consistency of your random numbers, so that if you run the same code twice, it will still produce the same random numbers. Okay, great. So I mean that's that. That's that part. I mean, maybe let me just look in the chat window. Yes, I mean, Matthias, yes, for each will still run on multiple nodes. I mean, that's precisely the beauty of this for each backend in ClusterMQ. ClusterMQ, this ClusterMQ register do par. You also see it's running. I'm just specifying n jobs equals 2, memory equals 1024. That means ClusterMQ will spawn 2 worker processes that can run on node X and node Y, and this backend, or when for each then comes along with all his work, ClusterMQ will distribute it over those 2 nodes. And I mean, I think if you go back to this little example here, maybe let's go to the file section. If we look in the open HTML code, open in web browser, then you see over here is the same example. And maybe let me just run it for you, so you also see that it's actually doing something. Let's open the quarter document. Okay, that's the quarter document. Let's just run all of the initial chunks. We don't need that stuff. We want to use the for each thing over here. So, and here we can do a little test. So now we have 1,000 samples on 2 jobs or 2 cores. It will run some things. So let's see what it's doing. Okay, that was maybe a bit too slow. Oh, but you see it's doing some stuff. Oops. Sorry, that's my little. I never know why it does that. Well, let me just open the session over here. Right. So let's go back to this little example here. Let's rerun it once more. Oh, sorry, that was the wrong chunk. Oops. We are at the for each loop. I think last time it took about 17 seconds or so. Let's see how long it takes now, or about the same amount of time. Yeah, so as you can see, it's about 17 seconds. Now let's rerun the same with 4 jobs. If my theory is correct, and it actually runs on different nodes, then we should see that this code is now running faster. Okay, you see it's now running in 13 seconds. Maybe so that yeah. Yes, absolutely. I mean, that's precisely why I think this for each backend of ClusterMQ is so powerful, because I mean it really opens the whole world. Yeah, and as you also can see, we also even haven't used any workbench jobs here, so that's that's available whenever you're on a system that is able to submit anything to HPC cluster. Cool, awesome. Great. So I think this is the cluster MQ package. And so there is a question for Manju again. Is this scalable with Amazon compute nodes? I mean, behind the scenes, what you have here is, Workbench is integrated in a Slurm-based HPC cluster that already runs in Amazon, and it uses EC2 nodes here. The technology that I'm using specifically is AWS parallel cluster. And I mean, there is, for those of you that want to explore things, look into the official page. But if you look in our Solenge GitHub repository, there is this repository here, which I will put in the chat box here. That's pretty much how this whole system is set up. So I mean, it uses Amazon compute. Yeah, I hope that answers your question, Manju. Yeah, and I mean, oh, okay, great. Yeah, and I mean, as mentioned, parallel cluster is using the Slurm scheduler, and the Slurm scheduler has a very interesting feature called power save. And the power save function was implemented even before it was run on the cloud for the first time, because sometimes those big supercomputing centers, they procure dozens of racks with hardware, and then sometimes there's peaks and troughs, and computers are not used. So because supercomputing also is correlated with lots of power consumption, those IT admins then want to have a way to power save. And so the Slurm has the ability to spin down computers if they're not used. So that was the original use case. And now in the cloud, it's still used as a kind of power save feature. However, both the spin up and spin down is now in parallel cluster tied to the Amazon APIs. Every time there's a spin up, it's not that designated EC2 instance to spin up. It's just that the spin up means I need an EC2 instance of this type. Go ask the AWS API and give it to me. And likewise, if it's not useful, it will be spun down again. So that's the basic principle behind that thing. Okay, cool. So I think we went through cluster MQ a little bit, and I think we saw that for each can run on more than one node through the beauty of cluster MQ. I would suggest that we maybe do another break till the full hour. We will come back, and then I will explain to you a little bit about a very recent package called future.mirai, because as you probably are all aware, this cluster MQ package is great for loop level parallelism with for each, and this Q function is all great. Well, but some of you also are more into object-oriented programming and functional programming. So that's where cluster MQ is not a good fit, well, but the future framework is, and there's the future.mirai package that we will talk about once we come back from the break is allowing you to use functional programming on a HPC cluster more or less in the same way than you do with ClusterMQ, but also with the full flexibility of having dynamic scaling and so on and so forth. And more of that at the full hour. So I'll be on mute. However, read any questions that you have, and we will be back in the full hour. And let's maybe keep going, because I mean, then I think I also want you to play around with things. So I think we've seen a lot of ClusterMQ working. I mean, the question of user of experience or recommendations for complex output with ClusterMQ would help. I mean, if you look at the output of a GLM, I mean, that already returns a complex data structure. I mean, by default, ClusterMQ will bind that into the list of all of those elements. I mean, for more sophisticated data structures, I mean, I definitely recommend you to look into the ClusterMQ homepage. I think that's probably beyond the scope of what we want to do today. Yeah. Okay, good. And okay, so Robert, however, William is taking too long, so I stopped them. I mean, if two people have the issue, maybe. Okay, I mean, let's do the following. I mean, first of all, because I prepared some stuff that is not on the slides. So those of you that are interested, if you look into the future.mirai sub folder, there's also our project that you can load. And there's also a pre-rendered quarter document that will show you a little bit how Mirai or the future.mirai package works. So you will find pretty much here the same function that we want to compute. And Mirai.
Michael, I think you need to share your screen. Sorry about that. Yep.
Yeah, sorry. I mean,
that's okay.
Great. Thanks for the reminder. Okay. So, I mean, what I didn't share, if you look at in the RStudio Pro session, there's a subfolder called future.mirai. If you open the HTML page, that's a pre-rendered HTML document. You see how Mirai works. So we have the same compute task over here, and the setup of future.mirai is still a bit maybe more complicated, but I mean, it's also not very far from a template. If you have it once, you probably can reuse it. So like with ClusterMQ, we have like 2 cores or 2 jobs here we want to run, and all the Slurm integration is done via this remote config thing where you have aspect commands, memory, and so on and so forth. I mean, that's something you just can copy like you want. And that will spin up all your worker processes in a Mirai cluster. And it also will return with 2. That means that it has using 2 workers. And once you have that, you will also see that Slurm jobs are popping up. Then, like with the future environment, you have to use the plan command to make sure that the Mirai cluster is available to the future environment. And then, like before, we were using the queue functions. We now simply use a future map function that is part of the FIR package, and it is kind of. I'm using a bit of a dplyr tidyverse notation here. So it's mapping the compute task functions onto those in the range of integers from 1 to samples. And it also, again, exports those packages, primer, penguins, and dplyr that I need within my compute task function. And that will produce the same result as before. And then you can do precisely the same post-processing again. Similar to starting those daemons, worker processes like with the daemons command up here, you also can stop them again via setting daemons 0, because that brings the number of daemons back to 0. To some extent, Mirai and ClusterMQ is pretty much similar, but it's Mirai is kind of the successor to ZeroMQ, the ClusterMQ is using, so it's much more modern, or actually, to be more precise, Mirai is an R package that uses NanoNext R package, which is the R frontend for the NanoNext messaging library, which is the successor of ZeroMQ. And in addition to that, Mirai is also used as an ingredient for the crew package that you may have heard of, that Rolando has put together. And this is all around asynchronous computing. That means this future environment here is completely asynchronous, and your computations will work here no matter on how many workers are up and running. So it's highly asynchronous. And you also can see that in my little rendering, I just started those 2 daemons, worker process, I used a plan, and you see the future environment realized, okay, my BI cluster only has 1 online worker, but it should have 2, so it gave me a warning. In principle, you could also add a statement here to wait until all of the daemons are up and running. So, I mean, those of you that want to explore that a little bit, take a look. And you also can, of course, open the Quarto Markdown document and run through the code chunk by chunk and see what's happening. And while you do that, maybe let's just make sure we either can get screen share of Manchu or who was the other one? Or William, I see you also had. Okay, so Phil or Harvey, can we wait?
Yeah, I can. Manju, I can promote you up to a presenter and then or panelist, and then you'll be able to share your screen. Okay. Do that now.
Yeah, I mean, those that are will become bored with the future Mirai stuff. There's also other things. For those of you that want to have a challenge, take a look into the remote ClusterMQ thing, because that puts ClusterMQ a little bit to its limits, because because I mean, ClusterMQ also can be used to remote submit to a HPC cluster altogether. So, I mean, you could sit in front of your laptop writing some R program and then using ClusterMQ to remotely submit your jobs via SSH to the login node of a HPC cluster, and then use Slurm to distribute it further here. And Rebecca, I will get back to your question in a moment. I haven't forgotten it, but remind me if I'm not getting back after we looked at Manchu's thing. Okay, cool. So, okay, I mean, that's Manchu's screen. So you actually posted 0021. Okay, that's good. Not 38, but now your job is kind of stuck here. Okay, so something doesn't seem to be right here. So can you click on the terminal here any studio? No, I mean, do not interrupt it. So now can you run SQ like the Slurm queuing?
Oh, okay, sorry, it's 21 here.
Yeah, I mean, just run SQ.
I don't
Yes,
need to type in SQ.
yes. This command that I just typed in the chat.
Oh, okay.
Okay, and then you see now you have now lots of things. So let's just filter out all of the other stuff. Let's rerun the SQ command and do using this command here. I will just paste it in the chat for a moment. Just have, yeah, okay. Copy and paste that command. That will only show everything that is running under your user account. Okay. Oh, that means that you only have one session running at the moment. There's no other jobs running. So now I don't know what's. Can you go back to the console, please?
Console.
Now within the RStudio ID, can you click on the console right next to terminal?
Okay. Yeah.
Great. Okay. So this is stuck. So something doesn't feel right. Oh, but okay. Can you scroll up a little bit in the console? Okay, that didn't go further up. Here. Cluster MQ. Okay, great. Further up.
Go down.
No, I mean that's all good. Okay, let's click on stop. Stop here. Okay. And in your code, you added that cluster MQ option.
Yes.
Okay. Okay. And maybe can you set n jobs equals 2 to make it a bit smaller problem? Although it may not fix it, but okay. Okay, can you run that stuff? Yeah. Oh, sorry, it shows the thing here. No, I mean you don't seem to be able to run any intact anything. William, it's the same behavior, and you're also just getting stuck here.
Maybe Mike can share his screen. William, right? William had a problem too.
Yeah, but I mean, I think William's problem is the same than yours. So I don't know what's going on here, to be honest. And you did the venv restore and everything?
Yeah, I did the previous code and then.
Okay. Yeah. I mean, yeah. But I mean, one should also look on the files section. I mean, you also see you have lots of slurm -something files. That also could be quite helpful for the others. So let's look at one of those .output files. Just click on one of them. What they tell. Okay. Because every cluster MQ or every Slurm job that is triggered by cluster MQ writes an output file, and that's a slurm-something.out. And you see, however, all of them are pretty much the same, so we do not even see an error message. So, Manju, can you stop it again?
Yeah.
And can you do a session restart? Can you restart your session? Just the R. Session restart R, yeah. Okay, let's fix it. Okay. And now, once it's back, let's rerun the whole thing again. Okay, go to your computer now.
Yeah.
Sorry about this inconvenience. Okay. Okay, that's good. That's good.
Is there this error worker disconnect monitor is disabled? I don't know what this is.
Yeah, I mean, this is just a new feature that by default is disabled. I mean, that doesn't.
Okay.
Okay, now let's keep running. Next one.
I just did the cluster MQ.
That's really bizarre. Oh, what I mean, I saw that the project is. Okay, so William.
Are banking on the compute of AWS, so I don't know if they are.
No, I mean, I think you shouldn't worry about the compute of AWS. I think that's all good. I mean, but I mean, I saw other people, SACT, other people were successfully running the cluster MQ example. Or can we get a feel with who has been able to run the cluster MQ example?
I can stop my sharing and
Sure. Okay. I mean, then I think I'm sorry I cannot probably be helpful, but William, and does it work for you now, or is it still the same?
you're talking to me?
You still need to install packages. Okay. Okay. So the package install with William is still going on, yeah? Okay. Okay, let's hop back to maybe, and I will share back my session. Maybe we can do it together. Okay. Well, but Ren, Manju, if you do Ren status, what does it report then?
So I mean, I don't know. I think Henry is saying he's not able to get the R session. What I'm thinking is it's just not being able to handle the load. That's what is happening with all of us getting there.
No, I mean, you will be surprised, Manju. Slurm is a scheduler that runs happily hundreds of thousands of jobs concurrently.
Okay.
I mean, if it would fail at this small number of users that we are here, would be quite surprised for. But Manju, can you try to run this random status thing and see what that reports?
Okay.
Oh, cluster's not well right now. Okay, and what is this queue? What is people running so red? I was able to run cluster. Yeah, so I mean, you see my little cluster internals, but we have enough storage space. Cannot get any answers. Yeah, what happens if I unsave?
It asked me to restart my status after the status.
Okay. Let's do. Okay, let's see.
Says like one or more packages recorded in the log file are not installed.
Okay, great. Now let's then do another run restore and see if it works then. I mean,
I can share my screen again.
sure. And Henry, as you can see, I mean, I can I can get into our session, so I don't know.
It says someone else is sharing. Oh, you're sharing, so I think.
Yeah, sure, sure. I mean, Mantra, maybe just do the new run restore and see if it is. So for William it finish the package installation, or can you try to run the cluster MQ example now?
Yeah, should I not worry about one or more packages are not installed?
Which packages are those?
It doesn't say that here.
And if you type run status again.
Okay.
Oh, great, William. So William can run the cluster example now. So I think you also should be able to soon. Yeah. Okay, Manju, let's.
Oh, okay. It says YAML package. Okay, I need to install it.
Yeah. So run install YAML with double quotes, or install the packages, whatever you prefer.
Mhm.
Sorry about the others. I hope that you still find this little debug a little bit interesting. And I mean, as mentioned, just as a reminder for the others, if you definitely can also study some of the other sub-repositories. And I mean, the remote cluster MQ thing over here could probably be quite interesting, because that also pushes cluster MQ to the limit where you could submit from your user workstation, your laptop, cluster MQ workloads directly to a remote HPC cluster via this SSH thing. So those of you that are maybe more technically savvy, we could take a look into that thing here. And I mean, this is also one of the a good segue, because some of you work for companies that have the full POSIT team stack that also include POSIT Connect, for example. And quite often you probably have compute intensive workloads that you want to run on your Connect server, but that's not an HPC cluster. So if you think that the RStudio session is your Connect server, then you could use cluster MQ to remotely run some of your heavy-duty compute stuff on the HPC cluster directly from your Connect server. Just for those of you that are maybe thinking a little bit ahead, yeah. Okay, about now back to you, Manju. Well, what's the status now?
So it's for some reason it's saying there is no library cluster MQ.
Okay. Can you quickly share back, because I mean I think you're still part of the panelists. Okay.
So
Okay.
it says there's no package called cluster MQ for some reason.
Okay. And can you try run? Can you do another run restore here to see what's happening? Yeah. You invite. Yeah. Now it's looking for all of the 60 something packages. We're solving that. I think this is. Let's see. Okay. I mean, you see, now I know why I mean, you all need to. Yes. Yeah, I mean, you all need to do the run restore. And I mean, the reason why it didn't work earlier, because the run restore is needed because it found other packages that it shouldn't have found. Yeah. Okay. Manju, just let it now that this is run. you can rerun library cluster and queue and stuff here. Okay, now it's much better. Okay, great. Now it's doing that stuff.
It's okay. This thing. This.
Yeah, it's perfectly okay. I mean, that's just a informative thing. And now it will, yeah, compute, go further, next one. You don't know how it should work. Yes, now you see it's doing something.
Yeah, now it's better.
Okay, great. Yeah, I mean, William, I agree. I mean, I shouldn't have mentioned it more explicit that the restore is always needed. Yeah. Okay, Yusuf is also in business. Okay, great.
Yeah, thank you so much. Appreciate it.
And I mean, that also applies to the other things. So if you want to share your stop sharing, then
Yeah.
you can continue. We can continue stuff. So all of the other projects that are in that Git repository, you see, they have all renv.log files. So if you open the project here, you do a renv restore, then you get all of the needed packages for that project, and then you should be able to run that stuff. All right, so I think that's that part now. Let me just see. Oops. No, I wanted to go back to the chat box. Is there any other questions? I think Rebecca had another question. Yes, I mean, Rebecca also asked a good question. Like you said, it was very fast to install the R packages when we do renv restore. How was the parallel setup? So this was set up precisely, maybe you tried a bit later, that was set up using the puck integration of renv. So that is puck.lib.org. Yeah, if I just go back to one of the very first slides, so I mean, this is the tool on slide 4. Yeah, so and the way how you make it work with renv is you either set environment variable renv config puck enabled equals true, or in your R code you also can set the equivalent options thing, like options. Let me type it here. Config.puck.enabled. Something like that. That's also possible. And I mean, and the good thing is that renv is aware of puck then, and it will automatically download puck and use it. And as you see, restoring our environments with puck is so much more efficient than it is without. Yeah. Also make sure that if you're on a POSIT workbench environment or on a Linux system, always also make sure that you're using package binaries. So if you look here on my little test system, I look repos, then you see that my current packages using public package manager that you have all access to, and they're using appropriate Linux binaries. That is also another way how you can speed up package installations, because if puck is still doing things in parallel, but I mean, puck is still efficient by parallelly installing even source packages. But if you can avoid the compile step and use directly Linux binaries, then I think that's also quite helpful. Okay, good. All right, then that's that thing. I think let me just get back to the other question. So we had that stuff. cluster. I think there was another question by you, Rebecca. I just tried to find back. Yeah. Can you summarize again? Rebecca also asked another question. Can you summarize again when you consider using Mirai? I caught you mentioning the limitations of ClusterMQ. So ClusterMQ is a very nice and efficient tool, as you all can see. It's by the Q function, you can also do lots of things by having functions executed in parallel onto those workers. It's all perfectly fine. Mirai, to some extent, is doing similar things. However, Mirai, and especially future.mirai that I showed earlier, allows you to use the future ecosystem. And with future, you can dive into the world of asynchronous programming. That is also especially useful if you think about my stretch goal, like this remote ClusterMQ thing. If you were to build the same stuff with a future framework, you could see yourself in a situation where you write a Shiny application on your Connect server, for example, and then via the future or future.mirai package, it would then remotely submit jobs to the HPC cluster. And because the package works completely asynchronously, then you can also have multiple tasks in the Shiny application and have the computations finish in parallel while you allow the users to do the other things. I mean, this is, as you can see, this is kind of also touching on the limits of my own knowledge about the Shiny system. But if you think about a use case where you would run those 1,000 samples of these compute functions with a Penguin data set, then you could write a Shiny application that would just submit that thing and then have a taskbar that would count from 1 to 1,000 or progress bar. And that's all possible with this asynchronous programming, which is not as straightforward as when you use ClusterMQ directly. So that's maybe my little blurb to that. I hope that this is sufficient here. Okay, yeah, and in terms of availability of the demo test instance after the workshop, I mean, if you all want to explore things today, and I mean, in principle, I can leave things up and running over the weekend or till Monday, if you like. However, I will later on briefly take down the cluster for maybe 20 minutes after the workshop has finished. And I will terminate all the sessions because I will make it a bit more dynamic. At the moment, we have, I think, 5 compute nodes or 10 nodes, compute nodes up and running all the time, and I want to make it more flexible. So if no one uses it, it's not harm compared to if people are using it. Yeah, to make it to ensure that we only use the resources that we actually need and no resources idle. Yeah. But what I mean is Monday next week, is that good enough for everyone to play around a little bit more? Okay, cool. And I mean, I guess some of you are abroad, or maybe by now most of you are in the US, so you have a whole day today for you. Yeah. Yeah, and same, and keep your user ID and password, yes. Okay, cool. All right, then I think that's, I know that the workshop now was a bit more busy with debugging, although I probably should have been more explicit with the event restore thing. But maybe just to go back to my little slides, and just end with the last slide that is giving you a bit of a high-level overview. So this is, I know this is crazy and complex a little bit. Here you have the Slurm workload manager, the Slurm scheduler that you've been using today in the workshop. And I think most of you have used ClusterMQ package on the bottom right to submit jobs. However, every one of you that logged into the POSIT Workbench environment also has used the Slurm to launch those sessions and stuff like that. Let's not forget about that. Those of you that are venturing into the future Mirai route, I mean, they will be using the FAIR package that is based on future, and then they use the future Mirai backend to talk to the Mirai cluster, which via NanoNext, which will then also consume the Slurm as a workload manager and also use NanoNext. And I mean, you also can see that there's many other avenues that you can go to use Slurm via the CRUD.cluster package that we didn't have time today to look at. Although if you look at some of Will Landau's presentations, you will find much more information and much better information that I will ever be able to prepare. There's another future backend called future.batchtools that relies on the batchtools package. You can use that as well. However, one of the possible problems you will end up with future batchtools is that it uses disk space for temporary files, so that depending on how you use batchtools can cause quite a bit of overhead. Like Mirai and also ClusterMQ, everything is in memory or in network, so it's much less overhead. And so now before we open to general, maybe last general Q&A, I just want to make sure that you're also aware of something that should maybe close out and bring back some of the memories, because if you look in the benchmarks section, you have a future.mirai subfolder. And if I'm opening the 50,000 file, then this is a little bit more of a complex code. And I didn't want to discuss that in great detail, but here I'm running this compute task function that you all saw a number of times this afternoon, using the future Mirai backend or the cluster backend of the future package, and I'm using always the same mechanism. Also always the future map with 50,000 samples, and there's a bit of code involved. And if you now look at the speed up that I get on running the thing from 1 to 64 cores, then you see with the cluster backend, the initial speed up is pretty much linear. However, you see after 16 or 32 cores, it becomes very flat, and it even decreases again the speed up. So that means if, for example, for 32 cores, you would expect a factor of 32 speed up. However, you actually only get a speed up of 8 or so, which is not very efficient. In contrast to that, the speed up with the Mirai package or future Mirai package is pretty much linear. And so you see at least between 2 and 64 cores, it's quite linear. So I mean, and that's another indication why instead of using the cluster backend with future, which depends on a monolithically launched cluster, using a Mirai is much more modern and also helps you to scale much better. Yeah. And I mean, if you if you look for the same results with the 12500 sample size, then this is this file. And you see here, if you put less work in your function, then you see the cluster backend is even worse. It already peaks at 8 cores, while the Mirai keeps going, although it also kind of flattens out at least a little bit here, between 32 and 64 cores. Yeah. And I mean, for those of you that are probably pixel people, or I don't know, I mean, it's, I mean, it was meant more of a fun remark here. You probably wonder why there is this little slow increase between 1 and 2 cores for the Mirai framework. And this is something that is part of the actual. I mean, this is due to the setup of the system, because on servers today there is a hardware thing called turbo boost or boost in general, where if a computer is not used at 100% level, the CPUs in that server can increase their clock speed way beyond the actual clock speed and will then be much faster. So that means that the speed up between 1 and 2 cores is not linear, but is less, just because that the 1 core result happened to be on a solo server where it had much faster effective CPU speed than with 2 and 4 cores. Yeah. And Asya, workshop for using a Mirai. Good question. There, if you look at the R and Pharma things for the last year or the year before, there is a workshop by Will Landau on using crew and targets, and I mean that also touches on Mirai. I also remember that there was another workshop at POSITConf in August this year, and I think, I'm not sure if that was recorded, but at least there should be slides available. If that's of interest, then I can send it directly. Yeah, very good. So Phil is on top. So Phil, I guess that's targeting, yeah. Yeah, and I mean, if it's okay with you, I mean, if people are interested, we can share a set of links with the participants after the workshop has finished, maybe early next week. Yeah.